Okay, welcome back. This is Mr. Hassan's Maths channel, and I'm now answering question number 6 from the June 2012 International, well, it's actually the old GCE Edexcel Mechanics M1, the 6677 specification. The mechanics specification hasn't really changed at all since the old and the new syllabus, which started in 2018. So these questions from the previous years are perfectly good to revise from. So I've been requested to answer this question number 6. It says a ship is moving with a constant velocity, the ship S, which is given by minus 12I plus 7.5 J kilometers per hour. Find the direction in which S is moving, giving your answer as a bearing. So it's going with a velocity of minus 12I and plus 7.5 J. Now the velocity vector tells us two things. It tells us the direction and its speed. The direction is going in and its speed, and the magnitude of this velocity would give us the speed, and the direction is given by the components of the vector. So let's just say it's here at that particular point. That means in 1 hour it's going to go 12 units to the left, which is west in this case, and 7.5 units north. So this is how its components would look. The component vectors would look for this. It would be 12 to this side and 7.5 up. So I've just, not really to scale, but I've just drawn something there. So the vector, the direction it would be going would be along this particular line over here. That's how it would look. So that's the direction of the ship S. This direction is 12 units to the left, to the west you could say, and 7.5 units up to the north. So we want to find this direction as a bearing. So it starts from this point over here. Okay, so I'm going to draw a north line at this point over here because that's where it's starting from. So this is the north line. Okay, so bearings are always measured from the north line, and they're always measured in the clockwise direction. So we're looking for the angle over here. Right, there's a number of ways we could find this. We could say, okay, if I know this angle inside, which I'll call theta, then what we're looking for is 360 minus theta. So this angle, I can find it by knowing that it's the same as this angle, because these are alternate angles, because this is north, remember this is west and north, so these are parallel lines, so these are alternate angles, so this is also theta, and I can find this theta because this is, as we said, north and west, so therefore this is going to be a right angle. So we can say that the tangent of the angle theta is equal to the opposite, which is 12 divided by the adjacent, which is 7.5. So we can say theta is equal to inverse tan of 12 over 7.5. So that will be the value of theta. So we do inverse tan of 12 divided by 7.5, 12 divided by 7.5. Close that bracket. Now we must make sure we're in degrees because bearings are measured in degrees. So that's going to give us 57.995 degrees. So theta is 57.995 degrees. That's not the bearing, however. We're looking for the bearing, and we know that the bearing that we're looking for, the bearing is going to be 360 minus 57.995. So we take our answer and we subtract it from 360. So 360, take away our last answer. That gives us 302.005, 302.005 degrees. So therefore, we know that the bearings are measured to the nearest degree. So that's 302 degrees. There's the answer for part A. Okay. Then it says, at time t hours after noon, the position vector of S is given by the vector S kilometers. That tells us its position with respect to the origin. When time equals 0, S equals 40I minus 6J. Write down S in terms of T. Okay, so that's what we have to do next. So write down S in terms of T. So that's basically the position vector of the ship at time T. And we know there's a formula for position vectors, which is R equals R0 plus V times T, where R stands for the position vector of the object at a particular time T, and R0 is the position vector of that particular object when T was 0, in the beginning of its journey, plus Vt. V is the velocity vector for that object, and T is just the variable t for any time that you want to find the position vector. Okay, so how this works is basically r0 is its position when time is 0. And they've told us here, when time is 0, the position of this ship is 40i minus 6j. So we know that r0 is 40i minus 6j. As I said, I like to use column vectors in my working. I always like to use column vectors and then in the end write it in this way. Alright, so that's the position vector of the ship at time equals 0. We also need to know the velocity of the ship. Now the velocity of the ship is given by, in this question, they've told us the velocity of the ship. It's minus 12i plus 7.5j. So we know the velocity is minus 12 and 7.5. Minus 12 at 7.5. So basically we need to put these two together and we can say that and r, the position vector of the ship, is s. So we can say s is equal to r0, which is 40 minus 6 plus the time times the velocity, which is minus 12 and 7.5. So there's the answer in terms of column vectors, but because the question gave us things in terms of I and j, I guess it's better for us to write our answer in terms of I and j. So we can say s is equal to 40 minus 12t, okay, I, that's the I component, plus minus 6 plus 7.5t j. Okay, you could write it in this form, you can write it in that form, you can even write it separately as 40i minus 6j plus, and you can say t times minus 12i plus 7.5j if you want. These are three different forms you could write it in. You know, all of them are perfectly fine. Okay, so there we have the answer to question part B. Okay, I just want to just give a little idea of how this works. Okay, just for those of you who have some doubts in vectors, all right, just to show you how this works practically. So basically what we have an origin. Let's say this is the origin. This is like where everything is referred to. So the position vector here is always referred to the origin. So 40 minus 6 is going to be something like, if you think about it, 40 minus 6 is not to scale, but say somewhere down here. So say that's where the object is at time equals 0. So that vector, that line going from there to there, that would be r0. So that's the position vector of the ship at time equals 0. And the ship is moving and going along in this direction with this magnitude. So minus 12, 7.5. So it's going like somewhere 12 to the left and 7.5 up. So it's going somewhere like this. Let me just, so it's like 12 across. Hold on, let me a bit better. Yeah. So it's going like 12 across and let's say 7.5 up. So it's going to be something like this. Okay. This is like not to scale, but just say that's how far it moves in 1 hour. I think this is in hours, right? Kilometers per hour. Yeah, hour. In 1 hour. Okay, so t equals 1 hour. It's going to be here. So this would be its position after 1 hour. This would be, you could say, R1. Okay, so to get to this position where it is after 1 hour, it's like you got to go R0 plus 1 times the velocity vector. This is basically the velocity vector. This is 1 times the velocity vector. Okay, it's like this plus 1 times that. That will take you to the place where it is after 1 hour. After 2 hours, it would go along that same distance, but from here. So after 2 hours, it will end up somewhere over here. This is not to scale, so it's not going to be exact. But after 2 hours, there's another velocity vector. So altogether, it's r0 plus 2 times v. Okay, so after 10 hours, it's going to be ending up r0 plus 10 times v, for example. Okay, so that kind of tells you how to find where its position is after a certain amount of time. So that would be the position vector of the ship after 2 hours. Okay, that's after 0 hours, after 1 hour, after 2 hours, and so on. Okay, after 3 hours, after 4 hours, after 5 hours. It tells you where it is in relation to the origin, how to get to that point in relation to origin. That's what position vector means. Okay, so that's an idea of how the position vector works in this type of context. Okay, so that's like a bit extra here. What we could have, our answers could have been any of these three, preferably any of the ones that involve I and J for our final answer, because the question was given in terms of I's and J's. Okay, now for part C, it says a fixed beacon B is at the point with position vector 7i plus 12.5j. Find the distance of S from B when t equals 3. Okay, we need to have our vectors for S. Okay, so here we have the vector for S, the position vector of S. We need to find the distance of S from B. Now we know that from O to B, the position vector of B, O to B is equal to 7 and 12.5, 7i 12.5j. Now that is fixed. That's a beacon that's fixed. So that doesn't move as time goes on. But as we said, this changes with time. Okay, so we want to find where the position vector of the ship is, or where the ship is in relation to the origin at t equals 3. So we can say at t equals 3, we can say that the vector from O to S at t equals 3 is going to be given by 40 minus 6 plus 3 times minus 12 and 7.5. Okay, so that will give us the position vector of the ship, okay, after 3 hours. So we have 40 plus, that's going to be 40 minus 36, which is 4. So just to make sure, 40 plus 3 times minus 12. That gives us 4, because you have 4 here. And you're going to have negative 6 plus 3 times 7.5. So we have negative 6 plus 3 times, this time we're going to have 7.5. So that's going to give you 33 over 2, which is 16.5. 16.5. So that's the position vector of the ship when time equals 3. We've got to find the distance of S from B when t equals 3. So therefore, if you think about that, what we can do is we can say, okay, say this is O, the origin. Okay, we know O to B is 7, 12.5. So it's going to be somewhere over there. That's where B is. And O to S is going to be 4 and 16.5. So it's going to be somewhere up here. Let me make a bit more space. So let's say this is O. Let's say this is B. So that's 7 and 12.5. And S is 4 and 16.5. So 4 and 16. So it's going to be somewhere up here. We don't have to do it to scale or anything. I'm just trying to do it a bit kind of on the accurate side. So that's O to B, and that's O to S. That's what we have. That's O to S. That's when time equals 3. Okay, so we know these vectors, and we've got to find the distance of S from B. So if I find the vector from S to B, okay, if I find that vector, then I can find the distance. Okay, so we know that this vector is O to B is 7, 12.5. And I know this vector is 4 and 16.5. Okay, so I can say the vector from S to B, I don't know why I put brackets there. No need for the brackets. The vector from S to B, if I want to go from S to B, okay, then I've got to go S to O, which is negative OS, plus O to B. So it's like O to B minus O to S. Okay, so O to B minus O to S, because you're going to go minus OS plus OB basically. So it's 7 and 12.5. Take away O to S, which is 4 and 16.5. 7 minus 4 is 3. 12.5 minus 16.5 is a negative 4. So we want to find the distance is the magnitude, the distance of the distance between 2 points. Okay, when you have them in terms of a vector, is the magnitude of that vector. So it's the magnitude of S to B, which is going to be found by the components of this. It's like this is a right angle triangle. This is like 3. This is like 4. 3 minus 4. It's a right angle triangle. So you can use Pythagoras. So it's going to be the square of this number here plus the square of this number. I don't have to worry about the negative sign because it's going to get squared anyway. So minus 4 and 4 both give you 16. When you square them, that's going to give you the square root of, that's basically 3, 4, 5 triangle. So we know it's going to end up as 5. That's 9 plus 16, which is 25. The square root of 25 is 5. So therefore, we can say the distance from S to B is 5 kilometers at time equals 3 hours. Okay, so there's the answer to part C. Okay, now there's an alternative way for us to have found the answer to this. Okay, we could have found the general vector that takes us from S to B at any time t. Okay, we could have done that. That's one thing we could have done, which I'm going to show you how to do. Okay, so the alternative way is to find the vector from S to B for any time t. Okay, so it's the same kind of thing. Let's say this is O, let's say this is S, let's say this is B. Okay, so we know that this vector here is given by this, which we can write as 40 minus 12t and minus 6 plus 7.5t. Okay, and we know O to B is 7, 12.5. So we can say the vector from S to B, as we mentioned before, is OB minus O. From S to B is going to be it's going to be minus OS plus OB. So it's going to be OB minus OS. Okay, from S to B, minus OS plus OB, which is OB minus OS. That's going to give you 7 and 12.5 minus 40 minus 12t, which is and minus 6 plus 7.5t. Okay, and we can work out what that is. That's going to be 7 minus 40, which is minus 33, and plus 12t. That's the I component, and the J component will be 12.5 minus 6, which is going to be 18.5 minus 7.5t. So that's the vector from S to B at any time t. That's how you get from S to B anytime t. So we can say that at time equals 3 hours, S to B is going to be minus 33 plus 12 times 3, and 18.5 minus 7.5 times 3. All right, that's minus 33 plus 36, which is 3, and that's 18.5 minus, let's work these out actually. So you have minus 33 plus 36, as we said, that's going to be 3, and we're going to have 18.5 minus 7.5 times 3, which gives you minus 4. So of course it's the same answer that we got before. Okay, it was 3 minus 4. That was the vector from S to B. All right, so therefore we can say that the magnitude of that vector is going to be the square root of 3 squared plus 4 squared as before, which is 5 kilometers. Okay, so that's the answer to this question. Now I've shown you two different ways of doing this. Okay, one is to first find the position vector of B at time equals 3 hours, and then use that so we find that position vector and then find the vector from S to B using that particular position. Secondly, I found the second way, this is a method 2, so I've shown you two different ways, is find the general vector SB for any time t, okay, which is this vector over here, and then substitute t equals 3 to here. Now this will help us for the second part of the question, because the next part of the question is actually going to be using some of these bits of information. All right, so let's look at the next part of the question. The next part of the question tells us, find the distance of S from B when S is due north of B. So again, I'm going to show you how to do this in two ways. First, I'm going to show you how to do it as if we found the, did it in the first way in the first question. All right, so I'll do with that first, and then I'll show you if we'd done it in the second way. And that second way actually would probably work out easier now because we already have the vector from S to B. Okay, so anyway, I'll show you how to do it in both ways. Okay, so let's say we had this is the position vector of S at any time t. Okay, and this is the position vector of the beacon. All right, when S is due north of B. Okay, if you think about it, when something's due north of something else, okay, if it's due north, okay, so if S is due north of B, then there's S and there's B. Okay, let's say that the origin is somewhere over here, 7, 12.5. Say the origin is somewhere over here. What we know when something's due north of something else, what we know is that the I components will be exactly the same. The I components will be exactly the same if they're due north of each other. Okay? That's what we for sure know, right? So the I components will be the same. So like this will be 7I, and that's for B, that's 12.5J. If S is due north of B, then it also has to be the same 7I for us to get from O to S. You got 7I plus whatever J, right? So if S is north of B, due north means exactly north of B, then the I components of the two vectors are equal. I components are equal. Okay, let me just move this around so my handwriting gets better. Okay, so therefore we can say, that the I component of the first vector, which is 40 minus 12t, has to be the same as the I component of B, which is 7. So we can say 40 minus 7, which is 33, equals 12t. So we can say 12t is equal to 33 over 12. Okay, that's the time at which they have the same distance. So we can say 33 divided by 12. That gives us 2.75. So 2.75 hours is when they have the same distance. But we got to find that distance. We got to find the distance. Okay, so we need to find the vector from S to B when time equals 2.75 hours. So what we can do is we can replace 2.75 in this vector. So we can say that the position vector of S at 2.75 hours is going to be 40 minus 6 plus 2.75 times minus 12 and 7.5. So see what that gives us. So we have 40 plus 2.75 times minus 12, which is going to give us, as we mentioned, we know it's going to give us 7. So we know that's going to be the same as that, of course. We know that. Right? That's like maybe a good way to check that you've done the right thing. But what we're interested in is the J component. We've got minus 6 plus 2.75 times 7.5. Now that is going to give us what we need. That's 14.625. So that's going to help us find what we need. That's 14.625. Let me just make that a bit neater. Put the bracket outwards. 14.625. Okay, so that is the vector that takes us from O to S. Okay, so we want to find the vector from S to B. So the vector from S to B, as we mentioned, is basically the vector. The vector basically is going to be the difference between the J components, but we can see the vector from S to B is going to be OB, which is 7 and 12.5, minus the vector from O to S, which is 7 and 14.625. And if you find that vector, of course, it's going to be 0. To get from S to B, you got to go 0, and you got to go 12.5 minus 14.625. Okay, so you're going to have 12.5 minus the answer, 12.5 minus the answer, which gives us minus 2.125. Okay, so of course we know the magnitude of this vector here is going to be 2.125, so therefore the distance is 2.125 kilometers, because this is just a straight line. So the magnitude is going to be that distance here, which is 2.125. That's the distance between them. The distance, we don't care about the direction, so how far they are apart from each other. So that's the answer to part D. Now, I mentioned I would show you how to do this if we had done the question in a slightly different way. So I'm going to bring up the information from that now. Okay, so the other method is if we had found this position vector, or not the position, the vector from S to B, how to get to the vector to the beacon from the ship at any time t, the general vector at any time t, then we could work out the same thing, because we know that if I want to go from S to B, okay, and I know that S is due north of B, how do I get from S to B? Well, I don't go if I'm going from S to B, I go straight down. So the vector from S to B is going to be equal to 0 and some value going down k. We don't know what that is. So therefore we can say that the horizontal component is equal to 0. The I component will be 0 in this case, because we now got the vector from S to B. We don't have to go horizontally, we go straight down to B. So I component is equal to 0. So we got minus 33 plus 12t equals 0. So that gives you exactly the same answer we got. 12t equals 33, sorry. 12t equals 33. So t is equal to 33 divided by 12. As we found earlier, exactly the same working here, 2.75 hours. Okay, 2.75 hours. And then to find the position vector, or to find the magnitude of S to B, we first got to find what S to B is at that time. So first of all, let's find what S to B is at that time. So we can say at t equals 2.75 hours. At t equals 2.75 hours, we can say you got minus 33 plus 12 times 2.75, and you got 18.5 minus 7.5 times 2.75, and of course this should give you 0, okay, as we know it does. Okay, and this is going to give us, let's just have 18.5 minus 7.5 times 2.75. That gives us minus 2.125 minus 2.125, and that's what we're looking for. That's from S to B. Therefore the magnitude of S to B is going to be basically 2.125. So therefore we can say that when S is due north of B, then I'll ask you to find the distance of S from B. S from B is 2.125 kilometers. Okay, so there's two alternative methods of finding the answer. One, the first one is if you had basically just hadn't found the general equation S to B first. You just found the position vector of S and the position vector of B, and when they're due north of each other, the I components will be equal, and you end up with this equation. The second method is if you had found the general vector of S to B in terms of t first, and in that case from S to B, when S is due north of B, then how to get from S to B, you go 0 in the I direction, so the I component of that vector is equal to 0, and then you get the answer in that way. Okay, don't forget, they're not asking for the time, and they're asking for the distance, so you have to go on to find the distance between them, which is the magnitude of that vector that we find. Okay, so there's the answer to question number 6, part D. That concludes this question. Thank you for watching. Other questions from this particular paper can be found in the playlist that should appear in this region here. Other questions from vectors in M1 can be found in the playlist over here. You can subscribe to the channel by clicking on the link that you'll find in the middle. Other questions from other papers and IGCSE papers can be found by looking in the description and clicking on the links there. You'll find index, index pages taking you to past papers or topic-wise playlists that might benefit you. Thank you for watching and see you soon.